Hi, I'm Tristan from the Samsung AI Center in Toronto, and I'm here to discuss our work on representing 3D shapes with probabilistic directed distance fields. Current approaches to neural 3D shape representations are either explicit, like voxels, point clouds, and meshes, or implicit, such as occupancy fields and signed or unsigned distance fields. Explicit shapes tend to have issues with fidelity, constrained topology, and scalability with increasing resolution. In contrast, implicit shapes avoid these problems, but are inefficient when querying depth in a particular direction, as it requires one, often, to find the surface intersection, which necessitates multiple forward passes. Our goal is to define an implicit field without this drawback, while still avoiding the constraints of explicit shapes. Our proposed method is called a directed distance field, or DDF, which provides an explicit field of distances to the nearest visible surface along any given direction. Given any 3D point P and a direction V, we can define a ray, R, which emanates from P along V. The DDF then consists of two fields: the visibility field, psi, which encodes the probability that R intersects the shape S, and the distance field, D, which encodes the depth along R at which such an intersection point rests, when it exists. In other words, the DDF is a five-dimensional implicit shape field, mapping oriented points, PV, to visibility and depth. One potential issue, due to the almost everywhere differentiable nature of most neural networks, is the presence of natural discontinuities in DDFs, when surfaces or occlusion boundaries are crossed. We obtain discontinuous outputs via a smooth network by returning a mixture of Dirac deltas instead of a single depth value. By taking the maximum likelihood component, smooth transitions in mixture weight generate discontinuities in depth. Thus, by fitting a coordinate network to a 3D shape, we obtain a representation that can be depth rendered with a single forward pass per pixel. In addition, we can obtain surface normals with an additional single backward pass per pixel and curvatures as well. This ability to obtain higher order geometry at a distance is in contrast with existing techniques that require many network passes per pixel. Lastly, we test our representation in a simple setting, namely the standard single image 3D reconstruction task, as this allows us to use 3D supervision along with off-the-shelf architectures. The basic schematic is shown here. Starting from an input image, we infer a camera pi and a latent shape vector z. To obtain depth and visibility, we pass an oriented point PV into an implicit coordinate network, conditioned on the latent shape z. Our results show that DDFs are a versatile and readily learnable representation, even without specialized architectures and when using a naive point cloud extraction technique for quantitative evaluation. We compare to an implicit point cloud approach, which uses an identical architecture except for input and output layer dimensionality, and obtain similar or better evaluation results, despite DDFs being a much richer representation. We also outperform a specialized voxel-based model and slightly underperform a specialized mesh-based one. However, we find that much of this error stems from incorrect camera prediction and that we can outperform the mesh-based approach when considering shape alone. Note here in the qualitative results that each pixel is the direct single-pass output of the network. In conclusion, we have presented DDFs, which provide a unified view of shape that captures all order of geometry at a distance and which can be thought of as a continuous implicit encoding of all possible depth images. In future work, we hope to improve on the scalability of DDFs, as well as the ability to better ensure geometric consistency with respect to viewpoint. We expect DDFs to be useful whenever fast directional queries of geometry are required, such as in AR/VR, haptics, or video games. Thank you for listening.